Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
I'm Zhen Yuzhan. It's my pleasure to introduce old Oliva, professor at MIT in the Department of Brain and Cognitive Sciences. I know Old for many years. The first time we met was 10 years ago at ATR, Japan, when I was on sabbatical there, and Old was a visiting researcher after her PhD. So Old had several positions in various institutions in UK, France, Japan, and now in the US. And I really enjoy her work, not only because his endeavor in understanding human vision is intriguing, but also he has done many nice projects trying to bridge human vision and computer vision. And today she will talk about scene understanding.
Thank you. Thank you for coming today. So, as you're going to see in my talk, I have a variety of demos, a little game to play with you. So let's start. It's coming. First, I'm going to talk about two topics that we are studying in my lab at MIT related to human visual processing, basically the way our brain is analyzing an image. And you're going to see there's a lot of bridges to make between human vision and image processing. And then scene recognition, which is basically how can your brain and the machine recognize the fact that this is a conference room or a street and so on. So scene understanding. And I'm going to start by giving you the talk I gave at SIGGRAPH last week. And this is a work in collaboration with Oliva Torralba from the Computer Science and Artificial Intelligence Lab at MIT and Philip Shins. So, hybrid images. What is that? So, I'm going to present a technique. I'm going to present a method that is going to allow you to create images that change interpretation according to different factors. For instance, viewing distance. So, let's look at this face. I don't know if at first you could see that the face is a little bizarre. You can see that the larger face represents the face of a woman, okay, with a neutral emotion. So now the other face pictures are exactly the same. I just changed the size. So now try to squint your eyes, remove your glasses, defocus, or just walk down the alley, and your perception might change. And are you seeing the angry man hidden behind the face? Okay. So this is not a trick of the screen or the computer. This is actually an image that is built in a certain way to show how vision works, and what you're going to see depends on distances, temporal frequency, and so on. So here is an illustration of the concept. Basically, what are hybrid images? You're looking at a picture, or it could be a video, something on the screen, and from a few meters away, a person is going to see one interpretation. We can do that with faces, objects I'm going to show you. And from another distances, the person is going to see a second interpretation. Okay, or you remove your glasses if you want to switch between the two. Here's a video where I just put together the same images, changing the sizes. So it's a way to simulate if you were walking towards the screen or further away. So now, if you are behind your screen and right now looking at these pictures, then you can actually play the game. So we reduce the size of the images in this talk to give you the effect that you can walk towards. But the effect is even better if you fix the screen or the viewing and you look at it from different distances. So basically, that's a method that is using, as I'm going to explain, the principle of human vision, trick a little bit your mind, and it's a way to create multiple meanings within the same exact images. And the quest for creating images with multiple interpretation, it's actually something science, art has been trying to do for a long time. So you all know the photo mosaic. You can create an images with two different meanings, or four photomosaic have more one global interpretation. So that could be a way to do it. Second way is you can create artistic photograph, like this image from Ian Butterworth, where you can combine images, and here you have two interpretations, the shoes and the butterfly, two global interpretation too. And here is actually an image we find a lot in the textbook of perception. What do you see? Tell me what you see. I want to hear voices.
A face and a saxophone player.
Exactly. So can everybody decide to see the face of a woman? Now try to look for the saxophone player. It's just a way your brain is going to organize the dark and the white part of the screen. Here they are, in case.
Oh.
So I just removed the eye to show you that the saxophone player is there. And for the face, you're just going to fill up the missing part of the face. So that's another way to achieve double meanings in one image. So actually, this is also, the double meanings have been something that painters have played with. So here is a painting from Alan Gilbert from, I don't know exactly the year of the painting, but it's like 80 years ago, 90 years ago. And if you look at the larger pictures, you see a woman looking at her reflection in the mirror. But actually, you can also interpret images, particularly from far away, as a skull. So here I change the size so you can see the two. And if you would walk now in the room and look at this picture, I bet that the first meaning you will have is the skull, and then you come closer and you will see the other interpretations. Also, in those images, even at a small size, you can still see the two. So you have to decide, oh, that's more woman or that's more skull. So now, this is also playing with interpretation, something that Da Vinci did with the famous painting of Mona Lisa. And this has been, I've seen this in the literature for a few years now. So apparently, if you look at this painting and you look at her eyes, so focusing on the mouth using your peripheral vision, you should see that she has a kind of elusive smile, kind of smiling. But if you look directly at the mouth, you seem to lose the percept. It doesn't work for everybody, but what happened is a researcher, Margaret Livingstone, from Harvard Medical School, put in evidence the fact that if you just decompose the paintings in subband, you can see in the lower spatial frequency band, the blur part of the images, that she kind of has a smile, a corner, like a shadows at the corner of the mouth. That is not present in the higher spatial frequency. And if you look at the big, large painting, it's an effect you can have. So basically, the smile will be gone as soon as you look at her lips. So that's a subtle effect, but it made this painting becoming very famous. So now, what are hybrid images? Well, hybrid images are also a way to create changes of interpretation. But the way to create them can be drastic, because now we are going to use the rules of human perception, the rules of human vision, to make them you seeing one interpretation or the other, and hopefully kind of decide and control this. So the thing is that even now, depending on where you're sitting in the room, you may start being in this incertitude area where you're going to see two things. I'm going to explain this in a minute. But from my distance, I see a dolphin, and that from far away will become a car, okay, and comes back as a dolphin. So what happened is we can, knowing the distance and so on, we can know approximately at which distances you will see only one, the others, or the two. And for some of you in this room, you may see the two, so don't hesitate to move towards the screen.
So what's the role of volleyball then?
The rules?
No, volleyball.
Oh, yes. Well, actually, the volleyball could become a stop sign. Let me play it again.
Oh, stop sign. Okay.
Or stop sign, why not? That's a sign. Okay, so how do they work? The principle is extremely simple. You take autofocus blur images, you superpose to the contours of another one. Okay? The principle is simple. how to make it work in any situation and have a control on it is what I'm going to tell you. So, human visual perception. This is what we do. Our brain is analyzing the images in a spatial frequency band. So here is just an illustration. It's like you are analyzing the images, taking blur images, like all the blur and the shadows part and the color, and then moving up towards higher spatial frequency, here illustrated by the contours. So now, image processing gave us very good methods to decompose an image in subband. So here is an illustration, the decomposition of an image in subbands. And what's interesting is we can make very precise link, thorough link, between the way we could decompose an image on the computer and the way our brain is actually decomposing the images. There are some subtleties, some differences that we're going to play with to create hybrid images. So basically, research has shown, and this is a curve that has been established in '69 and that is still extremely accurate, that called the contrast sensitivity function. It gives the spatial frequency ranges that human viewer will perceive. And below the red curve is the representation of the spatial frequency band. You can see the visible spectrum. So this function shows that the response of the visual system is a bit band pass. And it has a very low sensitivity for the higher spatial frequency. Basically, they're just a range of very, very high spatial frequency that your brain will see with difficulties or not see, and also somewhat low sensitivity for very low spatial frequency. So, what's interesting in this function? Yes?
Cycles per degree mean?
Cycle per degree, it means if you take 1 degree of visual angle, which will correspond approximately to the size of your thumb, it's about 1 degree, so 1 degree. Cycles, a cycle is an alternation of a white and black part, a stripe. So 1 cycle per degree means 1 alternation per degree. 6 is 6 alternation per degree. And they give you a measure of the sensitivity to which you're going to be, the level of sensitivity. So 10, 20, 30 cycle per degree is really very high spatial frequency because it means ta-ta-ta like a lot of lines. And 1 cycle per degree is just very low blur spatial frequency. And in human vision, we talk in terms of cycle per degree because we can relay that to this function. And then distances. This curve has a very interesting characteristic, is that it has this bump, and it has a maximum sensitivity that is about 4 to 6 cycle per degree of visual angle. So a thumb at the distance of the arm, 6 cycle per degree. And what has been shown is that this value is pretty robust, which is that first we can determine for each observer what is the curve of their maximum sensitivity, but also this can change, of course, slightly from person to person, depends if your vision is corrected or not, and can also slightly change with illumination. If the light is dimmer, you will be less sensitive to the sharp edges and details. So how is this related to what I just shown you, the fact that you could see different interpretations? So here is a simple demo. You're an observer and you're looking at a picture which is 20 centimeters high from 1 meter away. Your visual angle is about 10 degrees. So now, if you apply the sensitivity function, and we suppose you're the normal observer with a 6 degree of cycle of degree maximum peak, then here it is shown the peak sensitivity, which you can see is around, basically the contours, the sharp details. So now, of course, you're seeing everything. The world is normal because the curve is giving you all the range of information. I'm just showing to you here what you're more sensitive to. Okay, there's a peak. The peak is over there. So now, we take the pictures and we move it 6 meters away. It has changed the degree because the picture is smaller on your retina. So now the peak sensitivity can be computed and has switched to something that's lower spatial frequency. The same, everything looks normal because you're not running around seeing hybrid stimuli. But I can tell you, you will be more sensitive to that, that kind of spatial frequency in the image. So now, what happened with the hybrid images? Okay, we take two. You can see the original. And here is a cartoon. We take the low spatial frequency part, high spatial frequency part of the other images, and it basically creates a range of pictures, subband, that are different, okay? So now, look at the hybrid stimuli from 1 meter away. What are you going to see? You're pretty close. Yes. You're going to be more sensitive to that region of the spectrum. Everything seems normal. You're just more sensitive to that. Therefore, you're going to see the woman. Now, we move the hybrid images further away, and we can compute exactly those numbers for any size. Well, exactly, approximately. And in that case, this is exactly the same picture, but you're more sensitive to the lower spatial frequency band. Therefore, you're going to perceive more the man. So now, concretely, when we implement it in MATLAB on the computer to create them, we work in the frequency domain, in the power spectrum frequency. We're using Gaussian filters, but our filter would work. Gaussian filters work pretty well. And you can decide in cycle per images the cut you want to do on the low, cycle per images the cut you want to do on the high spatial frequency. Here, the high spatial frequency is the red curve, the low spatial frequency is the blue curve. And you can change the quantity of one or the other in order to have different percepts. I'm going to show you more examples. It depends what you want to achieve. If you want to hide information, if you want to have a long range of low spatial frequency, it just depends on the goal, but the principle is there. And something that is interesting for people studying human vision is that slide, actually, what we call the distance of switch. So, depending on the distance, you're going to see more one interpretation or the other. And we can have an idea where we are pretty sure, like 100% of people are only going to see the low spatial frequency or the high, if you will, like very close. And you have this region of uncertainty. So now, physics, psychophysics will give you a curve to tell you that the region of uncertainty can be between 3 and 7 meters. In this region, we don't really know what happened. Either, depending, you merge the two, or you cannot see one or the other, or you cannot see a third one. It all depends on the picture you merge. And the rules that are going to make this region of uncertainty or switch less is something that needs to be studied related to the principal grouping of vision. But that one exists. And you can make it more or less small or larger. And
so all you're talking about is just a linear filtering, no?
Yes.
Filtering.
Yes.
So there's no suppression, lateral inhibition.
The brain does that.
Any of those.
No, the brain does all those. But
let's say you have it.
here,
filtering.
it's only linear filtering.
So how? But in that case, it doesn't require any higher level of suppression.
That's a good question. I don't know where it is held in the brain, but V1 maybe could do it. But it's a good question. Yeah.
Does the alignment matter?
Yes, it's coming. The alignment is important. It's coming. I'm going to answer to this question. So here, actually, the little details that matter. So I should say that the work related to hybrid images is really in progress. So I'm going to give you some rule of thumb, some principle, and it needs more work and research. But those principles are, I think, can help you to do some type of concept. So in hybrid images, or whenever you're looking at something, the challenge is to look good in close-up. Because basically from far away, you're missing a lot of details. So, and there are 3 principles: alignment, perceptual grouping, and color, that can help the pictures to look better in close-up. So alignment. Here just took 2 faces, a cheetah and a tiger, merge them together. And the percept is could be ambiguous also from my distance on the screen. If you go closer, very close up, you will see the tiger. And in small, you have the cheetah. So I do not take care here of any alignment. And alignment, take your favorite method of alignment, morphing, transformation of your faces or pictures. And so here we had the tiger resembling in terms of the position of the local features to the cheetah. And here is the result, the line 1 on the right. So from far away, it will not make a difference, very far away. However, alignment is very likely to change the psychophysics curve of switch, in the sense that when you're going to work closer to the pictures, it's going to be easier to see the higher spatial frequency interpretation, so the tiger face. So you, or even maybe if you squint your eyes, you may still see better the cheetah on the red box than the green. So alignment is going to be a good option. And I'm going to show you an example where alignment was even better for faces. So here is it's a school example. The second one is a concept that there's no mathematical principle behind this concept. It's the notion of perceptual grouping. It's how your brain, with all the experience it had looking at the world, is going to group the shadows, the parts of the images to come to an interpretation. So in this picture, particularly if you're looking very close up, you could see a bicycle. But actually, a bicycle, and you have some shadows cast on the wall. But from a distance, the shadows are going to be reorganized to show a motorcycle. And maybe after the talk, you can walk towards those pictures to see the effect. So that's an interesting aspect, because our brain that is always seeking for interpretation, well, losing higher spatial frequency will just make up something. Yes?
What you explained by the earlier theory about spatial filtering.
Yeah, well, yeah, you still have the spatial filtering from far away. You're going to lose the sharp details that belongs to the bicycle. But in addition, perceptual grouping can help you to have a good percept from close-up view of the bicycle, and then because you interpret the rest as shadows and not as part of something else. So, oh yes, yes. You have a question?
Yeah, and it's interesting how you use the features of the wheels to in a double purpose. So it's the very fine details that make it look like a bicycle wheel, but it still has the broad, large scale, low frequency that helps you see it as well.
Yes. This one that was actually made by my colleague Oliva Torralba has a lot of, there's some artistic aspect in it. It's that, we tried a lot and there's something that comes up. But in this one, there's also another feature that's interesting, is the notion of, is the color. Because what happens is color is something that you will see mostly in higher spatial frequency at close-up. And here, color helps you to disengage from the motorcycle and go onto the bicycle. So those are additional tricks that can make the display, and color is one. And that's a principle that we can more. Okay, for far away, color is gone. I have more examples coming. A few examples of applications. Well, maybe just for fun, changing expression. So this is one of my graduate students. And she looks, well, how does she look? She kind of maybe, you see something that maybe not everybody sees. From my point of view, close up, she's kind of a neutral expression, but she's going to become surprised, or there's happily surprised, exactly. Maybe more in the middle range, you could see happy, it depends. So that's a kind of, so here are all the pictures. You can pick up the one you prefer. And there is no other manipulation than just an alignment of two facial emotion that Michel did. Okay, so that's an example. Another one is for texture superposition. There's a lot of method out there. It's not for competing with them. It's just to show you that you could superpose the textures that has the interesting characteristic to go away with distance. Same thing if you look at those those pictures from different distances. The hybrid and the original images from a distance will look the same, because because of this contrast sensitivity function, you will not see the superposed textures. And here I put actually the other images I used to do the hybrid and the transparency or morph, which will show still the features of the transparencies if you look at it at a distance or if you squeeze the images. So you can determine that the texture will become visible at a certain distance. And there's an interesting application for that are coming in a couple of slides. So now, large, very large, and the panoramic display. So the same principle could apply to, in theory, any size, even very, very large display, as long as you know the size of the images and those. So you have additional factors that are going to change your curve, which is atmospheric information, atmospheric, like if there's fog, or if it's raining, of course, the time, how much light there is outside, but the principle should apply. And something in relations with the fact that you can, your vision is losing sharp details as you go in periphery. So there can be some maybe ideas to come up between what you will see or not see in periphery, looking at larger display. And here's an example of another hybrid images that actually myself just before SIGGRAPH deadline. Maybe you see myself a little bit like a ghost. You will really have to be close up. I only exist in the color channel of high spatial frequencies. And if you start removing your glasses, I should be gone. And that's also, it's a distance effect. Here, the same images at different distances where the clutter is gone, and as well as the color. So there's just some principle related to how much information you want to give to the viewer depending on the distance or the size of the images, something maybe in information display or layers. Knowing also that, I'm going to show in a minute, you can train the observer to be very sensitive to one scale and neglect the other.
So in that case, it's going to change the filtering function.
Yes.
So is that subject to training at all? I thought this is part of the property of the system.
So that's coming. There's, we have done some studies to show that you could train subjects to be blind attentionally, because you have your visual system and then you have your attention. So your visual system, as I'm going to show it's coming, is processing everything. Why not? You know, it's all there. With the sensitivity function. So it's not exactly like a subband. But your attention is going to say, I discard this. And then you can train people to discard something.
You can only reduce the resolution, but not increase resolution. Actually, I work on hearing.
Yeah.
Yeah.
Exactly. So that could be the same idea. You could train people to be more receptive to one level of information. It's coming in a moment. So another, we went from the very large display, well, the tiny small displays. It's the same idea, because you could have on very tiny small display text that is actually going to disappear at a distance because you're adding some noise behind. So here is an example. It's a school example, needs to be worked on if you want to implement this in tiny display. But basically, you can use the same principle of how human vision decompose images, and you have this only peak of sensitivity to have a text that you can only see at a distance. Maybe I'm the only one, or you really need to be close up view to see that one. Huh? But you can add some noise in a part of the spectrum and have somebody just a couple of feet behind you being in the dark, basically, of what is on the screen. Same idea of working with those spatial frequency. As you said earlier, it's all linear filtering. You could have you could add complexities to it. You could add complexities, non-linear, and so on. So that's basically kind of a technique that is based on the rules of human vision that allow you to see different things depending on the distances. And it's also a way to show how human vision works. Because in the normal images, you will have maybe never noticed that you're so blind to far away, particularly if you superpose the texture of a cat on the face of a woman and you don't see it. So those are as a technique that we use as vision scientists to understand how vision works and can have some cool effect. So I'm going to spend about 5 minutes talking about some lab research with it, because we can do some laboratory research with it, studying the temporal dynamics of visual perception. So now we are going not to a large scale, we are going to very small scale, the temporal scale. What's going on after 30 milliseconds, 100 milliseconds, 200 milliseconds? You open your eyes. We build up hybrid images, but they are maybe not as fun as the one I've shown you. They are for laboratory. You can clearly see buildings superposed with an highway, and we can do that with any kind of scene. And we wanted to see what comes first. What comes first? What is your brain using first? So you can display images for 30 milliseconds on the screen. You masked it. That's a standard procedure in psychophysics. Put a second image, and people show something happening on the screen, and then they see the clear images, and they have to say the first things happening on the screen, the flash, was actually the same image, yes or no. So now, if you have seen the low spatial frequency, the city buildings, you will say yes. But if you happen to have not seen them, not had time to put them together, you know, it's very blurred, or if you have seen the highways that is proposed, you will say no. So that's the way where we can get a little bit. And what we observe is that for 30 milliseconds, people go onto the matching the low spatial frequency, so the blur part of the images. You move your eyes approximately every 200 to 300 milliseconds. So we really are at a time scale that that's really the beginning. Huh? You don't see 30 milliseconds all the time. Huh? So that's something we do in laboratory. And there's still a lot of time to the end of the blend to process everything. So we are really at the beginning. So now what happens is that when we put the presentation of the images to 120 milliseconds, we have a reverse pattern, which is that now observer will have the time to process the contours and will base their interpretation on the contours and will even not be aware that there's a city in the images. So it's a kind of the same idea that the distance, but put into the temporal domain. It's called coarse to fine, low to high spatial frequency processing. And as a psychologist, we are also interested in saying, okay, it looks like there's something hardwired there. We analyze the images in a certain way, we have a contrast sensitivity function, and we go from low to high spatial frequency. But can we flexibly, can we change this pattern? Can we kind of train people to see different things? And the question is, can we lock an observer on a spatial frequency band? So here is another example. If you remove your glasses, you will see more easily a far view on a set of buildings, city, and you have highway in higher spatial frequency. So what we did is we presented what we call RSVP, rapid sequence of visual presentation images, for 130 milliseconds, And in one group, people were having all the low spatial frequency images and were superposed to contours that had no meanings. So the only way to interpret images was to go on the low spatial frequency. In the other group, it was the contrary. They had meaningful images in the high spatial frequency band of the images. I'm sorry if you don't see it at your distances on these pictures, but the blue, the images at the bottom has a city in high spatial frequency. And then we can show the same images that has two interpretations on the low and the high spatial frequency and see what the group will say. So imagine you have been habituated to information at low spatial frequency. Another group has been habituated to information at high spatial frequency. Now I show to those two groups the same images. And they just follow their habituation. So this is what I was saying before, is that we could do a little training. And for about 10 to 20 images, people were not seeing the same thing, although we did not change the distances and we did not change the temporal frequency. We just changed the focus. That's laboratory work. It was good for 20 images, and then people were saying, wait a minute. and they start seeing the other. But it's possible to do this. And then there's some fun things to do also with faces. If you look at those, are they not the same to you? Well, again, depends on the distance. They look pretty like the same. It's a woman with a natural emotion. Or do you see something else? Yeah, there's some shadows, but
The shading.
the shadings, now it's coming, the shading is different. You want to squint your eyes, you want to go outside the room to see what's behind.
The right eyebrow is different.
Yeah, the low.
So, you have an happy and an angry man. Here should be angry behind, and here should be happy. That's low spatial frequency that are hidden behind. And with temporal frequency, we can also put them in evidence. So we have people looking at those pictures for a very short time, 50 milliseconds. One group just had to say if there is an expression on the face, just an expression, whatever kind of expression. Another group had to tell us the expression happy, angry, neutral. There you can try to play and see what's behind. And the third group had to say if it was a man or a woman. So the presentation time was fixed. And what we observe, and this has been replicated in other studies, is that our brain will have the ability to pick up the information where it has the most sense, and the spatial frequency range that will be selected will not be the same depending on the task. Because what happens is, from a distance, you're kind of used to interpret the emotion of people. Emotion is something we can see from very far away. So when they had to really say if the man was happy or angry, this is something you can get at looking at the shadows. So they were more naturally going on to low spatial frequency. But from gender, it was both. And when they just had to say if the faces was different than neutral, they were more on the high spatial frequency. So those are subtleties, details that we can study in the lab to see what's going on during this extremely short period of time with spatial frequency. Yes?
You're saying that for emotions, for expressions, for facial expressions, the perceptual of spatial frequency is more important than anything else.
So what happens is that if you have to determine if the face is positive or negative, which is happy or angry, that's something you can do easily with the shadows of the face. Because happiness is like the shadows goes a little bit outside, angriness, they come inside. So it looks like if you go on directly on the low spatial frequency, you have the information there that can tell you. So now, if you just have to say if the face has an emotion or not, why process the total? You can just get wrinkles or the mouth or the eyes. So what happened is that it's possible that when they just had to say if there was an emotion, they were people were kind of more focusing on the eyes or the mouth. That was enough, and this is something you have in high spatial frequency. And then they were giving the interpretation that was based on the high spatial frequency, which means that in this case they will say neutral in the task of saying if it's a neutral or not, and if they had to categorize it, here they would say happy. So, and last with laboratory, and then we go back to demos, is that we also discuss the fact that this kind of unconscious processing, what's going on during this glance, and one of the procedure is to show images one after the others. Here you can see a bedroom. Can you see superposed to this bedroom that you have a high spatial frequency of a city? You may have to come closer. So what happened is people were trained to categorize the low spatial frequency. Okay, so they did not know there was something in high. As a train, and they say bedroom and bathroom and street and so on. And sometimes there was something meaningful in the high spatial frequency. And when the next images had the same orientation in the low spatial frequency than the high spatial frequency of this one, we observe what we call a priming effect, which is that the recognition of this as a city in terms of reaction time was faster than when it was not preceded by an image with the same spectrum. What does it mean? It means that our brain, over time, with one from the other, is taking advantage of a kind of summary statistic. have a lot of vertical. If at the next glance have a lot of vertical, it's going to help me to process the vertical. So this is something subtle in human vision, but that can have some implication, as I'm going to explain in the next part. So now let's go to the second part of the talk. We have some information that the brain is decomposing the images in those special frequency bands, and actually you have those kind of global summary that are computed from one glance to the next. So can we learn from this to now study the notion of scene recognition and know how the brain is able to recognize that this is a city, a street, a conference, and how we can use those principles maybe to give ideas to machine vision. I have a lot of collaborators on this, and here you have their name. So what we are going to start with is demos. Okay? So I'm a fan of movies. I always go to the movie theater, and what I like a lot in movies are all those movie trailers. The movie trailers. Usually they are on the screen from, each image shot like this. You never experience any difficulties in recognizing what's going on, but the rate is very fast. So here I'm going to give you a rate. It will be faster than the movie theater. It's going to be 100 milliseconds per image. It's going to be like this, okay? And you're going to see the feeling you have in recognizing them. And my question is to see a cat. Is there a cat in the sequence? Hope it works. Let's go. Oops. I think it's a mouse things now. Oop.
Yeah.
Okay. 100 milliseconds approximately. Okay. Could you tell me the cat? How was it?
Gray, yellow, white.
White, black.
Yeah, white, black, gray, and
Arms extended forward.
that becomes. We can check later. So now we are going to see a sequence again. Look for the word Mexico. It's going to be large. Okay, so it's big enough.
Yeah.
Yeah. Right.
On the yellow sign. Black on a yellow sign.
Yeah, pretty good. Was the cat in the sequence?
Yeah.
Did you all see the cat in the sequence?
Two cats, though?
Yeah, actually, there's two cats.
One on
There are two cats. The first time, I think you all remember seeing the front view of the cat. Well, the cat looking at you. There's another one where it's tilted, but there's two cats. So when you do that day after day, you become better at it. You can see a lot of things. So anyway, there was only 100 milliseconds. No problem. No problem for saying this. Okay, but that's not very fair. You're not walking around looking at things for 100 milliseconds. You have plenty of time to look at them. So let's look at them. Okay, look at the scene. That was 10 seconds. Okay, did you notice anything?
You changed something
Oh.
during the 10 seconds.
Okay, what did you see?
There's something popping up and then going on.
What changed?
To the right to the left of those two men, the storefront, the white storefront, it was something else, and then you changed it to white.
Didn't notice
So-
anything.
Have you seen this?
Yeah, I saw that. But
Is
I
that-
don't know what it is. There's some change there, but I don't know what it is.
Okay, good. So some of you, have you nothing? I mean, most of the time, 50% of people see absolutely nothing. But
No, I didn't see it.
you had 10 seconds. A glance is usually 200 or 300 milliseconds. Okay, let's look at it again. Oh, I did wrong. You saw it's coming again.
The yellow one goes.
Yeah.
Is that what you did last time? Is that the same as the first
That was
time?
exactly the same. Good. Good. So, I think I could, but the last time.
That's why I didn't tell us where the phone. Right.
But you did not expect, well, you may expect it that something will happen, but I think this is an illustration of how blind you are to the world when you have plenty of time. Again, I tried. There are a lot of changes. Go ahead. Look for them.
Something appearing in front of over
Now
here.
you're a bit.
So if you blink it, I'm sure we can see.
Here are all the changes.
Wow.
And you can see, so people disappearing, the patisserie becoming a CD player, a CD shop, music shop, colors, and so on. That's a lot of pixel in the images. And when people are not expecting something like in a talk, it's a good 70% of people that don't see any changes. So it's just an illustration of how your brain and your visual brain is going around the world.
So you think just the prediction that makes people blind?
That's more so.
This prediction, because people are not expecting anything, so that's why people don't see
There are a lot of things going on. First, of course, you don't expect things changing like this because it's not a statistic that your brain is used to. You know your brain is a statistical machine. It's learning. It's not learning that things are going to disappear. If you are in a virtual reality system, you may wire your brain differently. That's actually a very interesting aspect. But most of the time, your brain did not pick up on those changes. The other thing is I'm going to show in a minute, there's studies in lab are trying to understand, and also in my lab, what's going on when you're looking at something. When you're looking at something, what's going on to the rest? Because your attention, not your eye movement, your attention is moving at a speed about 40 milliseconds. 40 milliseconds every move, between 20 and 60 milliseconds, let's say 40. So during this move, you gather a lot of information. But you have a problem in memory. So maybe you see it, but it's gone. Or maybe you don't see it. So
people are saying that human eyes are very sensitive to the motion, right? To the motion,
Yes.
to the movement of the scene. So in this case, like if I look at the building, I mean, a lot of us just now were blind. But if there's actually somebody was walking, I'm sure everybody will notice it. But some parts of it started to disappear, but people don't really notice it. So you think that's not really part of motion compared to the human walking?
That's a good question. We are also, us in the lab and others in the field of visual cognition, have tested a lot this phenomenon with motion. Because motion is something we pick up. So what happened is, I'm sorry I don't have the demos here, but I can send you some web pages. If you have a lot of things moving, your attention is going to lock on something. The rest is moving. You could have a white cat among black cats, something enormous appearing in the scene. If your attention is not there, if it is dancing, you will not see it. There are some great demos. I'm sorry, I don't have the demos here. So what happens is, if everything is static and you have a motion, it's called a saliency effect. Saliency, it's going to call you. But if you have n motion going on, and you're interested in one, if something happening, you're going to be blind to it. Most of the time. You can train that, by the way. You can train to... that's something I just want to tell you there is that there are some studies with video game showing that video gamers, this is what they are trying to do all the time, like seeing a lot of the object moving and reacting fast. Their sensitivity to those changes is much lower. Basically, they see them almost all because they have trained their system to be sensitive to a higher spatial temporal frequency environment. So that's something you can train. So the common sense that we have when we think how the brain composes images is called the constructive view of scene perception. And here's a little cartoon. Those slides come from Professor Wolf, Jeremy Wolf at Harvard Medical School. And what happens, you open your eyes, and studies have shown that for, I don't know for how long, those milliseconds, you have a kind of summary of things. You did not form an object yet. You know, you're not staying 200 milliseconds on an object for nothing. And your attention will go and called binding from object. Okay? So that's a very appealing one because you're observing from object, from object, from object, but it just happened to be wrong. What studies have shown is that instead, here's the world, you go somewhere. So this is to illustrate the movie you have just seen. Okay? You see two people walking. Then you move your attention or eyes, depending what you're moving, the speed, to another object. Look what happened to the previous one. Studies have shown that the previous one goes back in a state of kind of summary. That's a cartoon, but it really illustrates what studies have shown. Then you go to another one. You formed it. Remember, the speed is 40 milliseconds per object or per zone. Then you go to another one, and the other one goes unbind. Another one, there, 40 milliseconds, that's a slow one. By the way, what was there? Which kind of object was there? Green train. What else? You don't know.
It's just a guess.
You don't know. So there are several things coming up. Perception. You unbind the features when it goes away, but you also have some memory. There was that guy. So you will have to go and check with your attention or your eyes. And those are studies we have done also with scene. So basically, what we are doing is we move our attention, we bind an object, and the rest is a kind of a summary. But you're not conscious of that. Consciousness arises twice a second. We are really and those can give us useful features and principles and ideas for now computer vision. And I'm sure I can do the rest in 5 minutes because I don't have any more demos, and demos are usually what's fun. Okay, so scene gist understanding means that our brain is able to understand the meaning of an image just looking at it for 50 milliseconds, 30, 100 milliseconds. It's called the gist, the summary of it. And the approach we have been taken in the lab for now years is if you want to build a machine vision that is going to recognize that's a path through trees, the strategy that has been used so far is, well, let's look at the textures, let's segment my image, let's find out I have trees, trunk, leaves, and so on. But what human vision is telling us is that we are kind of going a lot by those summaries, what those summaries could be. So we are looking at those. Is there another way that we could implement image recognition, but instead of segmenting the images in object, something we also do down the road, I mean, we'll put that in memory. We look at a variety of others information about the scene that are going to give you a global summary. For instance, there's a path. It's a forest. It's big. So properties that we call global properties or global scene analysis, natural space, enclosed space, perspective, and so on. And the hypothesis we had is maybe our brain could use as a complementary path. I'm not saying that we're not computing objects. Of course we are computing objects. Those global properties to get at the meaning of a scene. So what we had people that were organizing pictures in group, and they had to make groups that were not following the object in the scene, but were following those global properties, something to tell me about the scene and the space. Like I can move in it. It's complex. It's natural. But nothing related to the object themselves. So man-made natural structure, or there's some perspective, or it's something far away. This is an open, a panorama, and so on. And from human subject, we got a list of properties that we call spatial envelope properties because they are talking about the scene as a whole. So here it's a scene that has a medium level of clutter, that is enclosed, that has a small path, those level of descriptors. I did not say chairs, I did not say people, that levels of description. Naturalness, the depth, openness, panorama, the perspective, the potential for navigation, and so on. And we have human subjects organizing pictures, hundreds of pictures along those different dimensions. So here's an example for mean depth. Mean depth is my view is close up or far away. Okay? It's like if you look down, that's a close-up view. You look at, I don't know, like a beach scene, this is a panorama. And we had the ranking like that from human subject on those dimensions. It's just telling you something else about the image. We also had them for other interaction you can have with the space. You can walk in, you can hide. We are still at the human level. And here is the hypothesis. maybe all those properties are telling us the semantic category of the scene. Because maybe they are statistically constrained enough that if I say this is a urban space with a mirror symmetry, a lot of perspective on both sides, vertical structure on the left, on the right, are not you thinking about the street? That's the same level of description. We have not said buildings or cars, that's another description. And the idea is, can we have a global analysis that will give us the semantic category of the scene? And this is the work we have done with Oliva Torralba and Michel Green for the past few years. And where we came up with description of the images, not in terms of the object it contains, but in terms of those descriptors. And the result you see here, this is a machine vision system. Now we move down to a machine vision system that has learned the features, the statistical summary that are telling that you can navigate, are telling that there's perspective, telling there's openness, and so on. And transform those features information. Those are image processing. We can use machine learning methods behind. And to go from a space of features to a space of word, and then a categorization procedure. So those are results from a simulation we have done. And we can also organize images in semantic concept, where we observe that pictures that are similar, semantically, there are streets, or there are view of buildings, or there are forests, or beaches, and so on. They also have similar type of those global properties. Because a street for cars will have a level of perspective, a level of symmetry, a level of textureness, and so on. And those might be robust enough to have results like those, and could be something our brain is using to get at the interpretation of the images in 50 milliseconds or 30 milliseconds, extremely, extremely fast. And then we use this to implement a model that compute the gist of the scene, to have an idea of the structure of the images, like it's a row of houses. We can learn the association existing between a scene and object, and so work done with Oliva Torralba, have some local features, and start predicting eye movement of people. Where are the eye movement? The observer, we have an eye tracker, we're looking for people in the urban scene. About 1,000 different urban scenes with different viewpoints and so on. So we have the human in red and the prediction of the model. The model just predicted the location based on those global statistics, like the level of openness and so on, and so what called the context. So I think I went very far there because the demos were more fun. Those are the other things we do in the lab, and thank you very much. I'm going to end there.
The last slide will show so you will try to eye gaze. I mean, we're trying to decide what kind of features you are looking at.
In this model, we are learning the association existing between the features that represent the structure of the image. For instance, you know it's a street, and the location of the object. So that's a learning part that you do beforehand. You learn the joint probability existing between one image, kind of n images, thousands of images, and the location of people. So then you have built what we call a prior. And the model has also information about what is salient in the images, because there is a fact our eyes is going to be guided towards a region of the images that are different from the rest. It's called the saliency. In this model, we combine the prediction that the model will make. Oh, I see it's a street. I predict the location will be over here, with the part of the images that are salient, because we do know that the eye is going to like that too. Then, when we combine the two, this gives those regions in yellow and greenish, and this is where people go to find the object. So what happens is we tell people, look for a pedestrian. they go into around this region. And the model that has previously learned the association existing between the features of the images and the location of the object pedestrian is going to alight this zone. And then we can just look at the overlap. So for instance, we did it also with cup. Cup is a difficult object. A cup, a mug, can be everywhere. So that's also... I went very fast. I can talk with you about this. Yes. Yes.
So on where we were looking for the cat, that was 100 milliseconds, right?
If the projection is right about that. Yes.
Sure. Now, what if we were to speed that up? What's the minimum number of milliseconds that the typical audience would need to see the cat or see the Mexico or whatever? 30 milliseconds, or how do you know?
Okay. So let me think. First, there are curves that I can dig for you. I can find the curves. 100 milliseconds, you will see it. 50 milliseconds, I think you will still see it around 70%. Then it depends on what you put. For example, if you look for a cat among tiger.
It's harder. Yeah.
Okay. But if you look for a cat among object different,
sure.
I would say 30 milliseconds, but I'm going to go and check. And this is, as always, if you have 50 sequences, it's going to be a probability. But I would say 30, you have a good amount. 100, you're pretty sure. And the glance is 200, which is on average how long you spend. I have another movie. So that one, the thing is with the projector is, that's another one. Okay, let's see, look. Okay, I'm not going to say what you look for. You're going to remember something. Okay? Okay, yeah. Okay.
Monkey.
Yeah, everybody. Let's do it again. That one is salient in a temporal way.
Is that sort of like which one of these things is different, the most different?
So what happened is that we can have some good estimation of the similarity existing between images. And in this case, the monkey, when it comes up, the picture before and after are different. So it's going to be boost.
Yeah.
We could do it in 30 milliseconds. I think it would be pretty good.
What speed was this? 100?
It should be around 100, yes. I have on my computer 50 milliseconds that I can show you later. So what happened is faces are salient by themselves. We have so much learning with them that we have some hardwire brain region discovered by Nancy Canwisher, a professor in my department, that are 4 faces. So faces, even faces of animals, are a little special. You might not get that well for other objects. There's actually 2 monkeys. You have another one. Have you seen the first one? It's at the beginning there's another monkey. The little one.
The third or fourth string.
So those curves exist, and a lot have been established by Professor Molly Potter, who's also in my department, and she has papers with the curve and telling you how much for a certain presentation time. Yep.
Me again? Okay.
Yeah.
This is fascinating because because not only do we see, yes, there's a monkey there, or yes, there's a cat, but we can talk about things that we observed about that cat in those 100 milliseconds. So when I think about like browsing and information retrieval, right, this is just more evidence that it's extremely much more efficient to use visuals than text if we want to browse for information. And do you know of any papers that have documented how much richer, in terms of high bandwidth information, the human being is taking in with visual images versus text versus speech versus touch? Do you have computer studies?
I can give you some names of publications that have looked at images and text.
Yes.
Which those, and this is the same person, Professor Potter. I tell you, I can tell you right now. I tell you later. But in a minute. So yes, Professor Potter, Molly Potter at MIT has done, and there are some other names I can give you that have documented this. We are also working on this in the lab, except that we are not checking text right now because vision can keep us busy. But I could tell you that reading the visual world is what we call automatic. You cannot not interpret it. It's very fast, you're going to recognize it. And you can work on those sequences extremely fast. For instance, you're looking for a cue. Your brain can have a good 100 millisecond per image, ta 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 ta, and will see it like you have experienced yourself. Words needs to be read. Words are beyond those processing. They are at the eye movement level. This is slow. That's a 200 or 300 milliseconds. For words. One word, if I tell you, but if you have a series of words, it's going to, just because the similarity between letters is closer than what you have in terms of the richness of the visual world. So at the end of the day, it can be similarities between what you're looking for. If you have a red word versus a green one, if you see both color, that will be okay. But on average, text is a bunch of orientations. That's it. So it's something that we have the text, the hybrid text here. So you can find some parameters for that. But pictures is worth 1,000 words.
Yes.
Yeah,
Yes.
that's mine.
Yeah. On the other hand, the words can describe this complicated, this abstract concept.
Yes.
I think it's not able to describe.
So here the one was one word.
So what is also amazing in using a human observer to interpret images is that, if I just put one, is that we can relay on our memories and a lot of information. So what is a little bit, we don't know yet how much you saw from how much you deduced. Okay? Because if the statistics of your world are coherent, if I see one row of chairs, I just duplicate. So maybe I've not processed all the information of all the rows. I just saw some rows. Then I put together. Our brain is a machine that is running on the past statistic. So this is why you did not see what's going on with the cars, the things, because statistics are not telling you that the world is going to change. But if the statistics are coherent, which is 99% of the case, then you just need a little bit and your brain will do the rest. So what we don't know is how much your brain is in all the inference. It does a lot. It still does a lot because it can do it at 50 millisecond infer and so on. So there are some studies that show those pictures for 50 milliseconds and ask people describe them. Give me a description. And sometimes you're absolutely sure you saw something. It was not there, it was just makeup.
So you showed images of hybrid images. I was just curious if you can make like a hybrid video, if there's animations where the two things, as long as both of them are moving around. But somehow you
Yeah. So in theory, it's possible. In theory, it will be possible because you could follow up a motion. Oh, certainly from far away and close up. Yeah.
That's right. It's just like
there's a movie.
This lady moves somehow.
Yes. So from far away, you're only going to see the low spatial frequency movie. That's not a problem. To have a movie with a certain. When you come closer, you're adding like a third dimension to all of this. You're adding the dimension of motion. And it will, in theory, it's possible. We have not done it yet. But it's going to be more challenging because your brain like motion.
Right.
So you have to suppress the other motion. I believe yes. The same principle is just more challenging to put. But the answer should be yes.
So when I'm talking about the spatial filtering,
Yes.
how does color enter into the picture?
So
Is it independent channel or is it sort of color? Because I noticed a lot of things you're having here, actually color makes difference.
yes. So in this case, we use the low spatial frequency part of the color. I mean, the color on the low image spatial frequency and on the eye. So in this case, color was also part of the filtering. But on the motor case, we did not use the color of the motor. The motorcycle originally was red. The one you see here was red. So in this case, like we wanted this illusion of shadows, we did not use it. So it all depends of what you want to achieve.
If you had painted red, it would not have worked so well.
No. I think that it looks like the wall is painted, but you think it's a little bizarre. I mean, you cannot get onto the shadows interpretation. What is elegant with this one is really in closer view, like me right now, or if you look later at the CD, I mean, this is just a wall of shadows. In this example, it's particularly striking if you move towards it. The color is gone at a certain distance, or if you just squint your eyes, because in this case, we put color only on the higher spatial frequency channels, so it can help you to form the pictures. You could even think that I am almost normal when you're very close up view. I kind of exist in this image, but I only exist at a spatial frequency, and you can see some of the reddish, bluish, that will be gone if you squint your eyes or reduce or walk towards it. Yes?
The color space?
Very good question. We did not try. Here it's just RGB. Maybe there's some fun stuff to look at it. I don't know. Okay. Thank you for your question.